Okay, so on this project, we're looking at related rates of change problems. I chose number 33 as a problem out of the book, and this is what it says. A baseball diamond has the shape of a square with lengths between bases at 90 feet long. A player running from second base to third base is moving at a speed of 28 feet per second and is 30 feet from third base. At what rate is the player's distance from home plate changing? Alright, so as you can see here, I made a baseball diamond put all the given information on it. We have our 90 feet between bases here and our 30 feet from third base from second base here. And the question is asking your rate of change from here to here. So at what rate is this distance along our line here changing? So what rate is this line at? So we're given here that we're moving at 28 feet per second, but because this is getting smaller, it would be a negative 28 feet per second. So then you come to the next side here, you can see I pulled out this triangle, and we're missing a lot of pieces. We're missing this length here, which came from this piece, and then we're also missing our rate here. So I'm going to go ahead and start out by using the Pythagorean theorem to find this distance, because if we have this distance, we can find the rate of change of that distance, or how quickly that distance is moving. So I'm going to start out here with a squared plus b squared equals c squared. And then we will come back to this equation when we need to start deriving. We're just going to go ahead and plug in 30 squared plus 90 squared equals c squared. And then simple algebra, solve this out. Get 900 plus 8,100 equals c squared. 9,000, take the square root of that, square root of 9,000 equals c. So our c equals right around 94.87 feet. So we're going to go ahead and put our 94.87 right there. Then, given that information, what we know is we need to find a related rate of change of this length as it relates to this length. So as we're moving in this direction at 28 feet per second, how fast is this changing? Because if we go back here, we know this distance is changing and this distance is changing, but then we can also see that this distance stays the same. So we don't have a rate of change for this 90 piece here. So this piece is just 0 feet per second. Then, so now that we have relationships between this side length and a rate per change, this side length and a rate per change, we simply need to find the relationship between this side length and whatever its rate of change is, because that's what we are looking for in the problem. To find, and it's all related, so this is a right triangle, all the sides relate to each other, so all the rates of changes relate to each other. So we can go ahead and use this Pythagorean theorem equation, add our chain rule in there because we have to derive it. So we end up with 2a dA over dt plus 2b dB over dt equals 2c dC over dt. And then we're deriving in terms of a rate per change, so we're deriving in regards to time. So then we can just go ahead and plug in what we're given here. We're given our A, we're given our B, and we have our C. We have our DAD, have our dA dt are dB dt, and then the only piece we need left to find is our dC dt. So I'm going to go ahead and plug in 2 times 30 times 28 plus 2 times 90 times 0 equals 2 times 94.87 times dC dt. From here, we just simplify this out. And this is a negative 28, remember, because that's getting smaller. So we get a negative 1680 plus 0 equals 189.73 dC over dt. Simple algebra, divide by 189.73. Divided by 189.73. And you get the answer of negative 8.85 feet per second. Which this would be your dC dt, because that's what you solve for, and that's what this rate of change is. So this is the answer to your problem and how to solve it. Gigi, what do I do to stop recording? Stop recording.